new lecture on phase equilibria, which is lecture number 17. So we'll just do a brief recap of what we have done in past couple of lectures. So in past couple of lectures we saw free energy versus composition diagrams. So free energy composition diagrams basically are the diagrams in which you plot the free energy of various phases at a constant temperature as a function of composition, and when you vary the temperature and look at the variation in these curves, the relative movement of free energy composition curves of different phases, they define the new equilibrium for existence of phases. So free energy composition phases, if you vary them at various temperatures, you can construct phase diagrams from them. And depending upon the type of system that you have, whether you have complete miscibility of A and B in each other, or they are partially miscible in each other, or they have immiscibility and so on and so forth. So you can draw things like, you can have isomorphous phase diagram. Isomorphous phase diagrams were the ones where A and B were completely miscible in each other in both liquid and solid states, which basically meant that delta H of mixing was very low and A and B liked each other's company. And then we had case of eutectic phase diagram. In the eutectic phase diagram, typically A and B are partially miscible into each other, which means there is certain amount of solid solubility of B in A and A in B, and that is because they have certain size differences, they have differences in structure and valences. As a difference, as a result, they make a solid phase diagram in which you have two terminal solid solutions A and B, and then you have in the intermediate region, liquid has a minimum melting point at a temperature called as eutectic temperature, and at that eutectic composition, liquid completely transforms into mixture of solid. And then we looked at another one called as peritectic phase diagram, and in addition there were some other phase diagrams that we discussed. So for example, eutectic phase diagram is something like this. So if you draw between for A and B as a function of temperature, then this is the kind of diagram you get for eutectics. So this is liquid plus alpha phase, this is alpha phase, this is beta phase region, liquid plus beta, and then what you have is alpha plus beta phase region here. So so this is basically a eutectic phase diagram where A and B do not have large difference in the melting points. They have partial solid solubility for each other in the solid and liquid phase, and this is constructed by looking at the free energy composition diagrams at various temperatures. Then we have another case of phase diagram called as isomorphous phase diagram. So this is the isomorphous phase diagram in which you have liquid region, then you have liquid plus solid, and then you have solid. So solid and liquid, so A and B are miscible into each other across the whole composition range. And then we had another case of, so this is isomorphous. And then we had another case of peritectic phase diagram. Oops. So this is basically a straight line. Let me just redraw it. Okay, and then we have, so you can have, so this is temperature, and so this could be liquid all across. So let's say this is liquid plus alpha, this is alpha region, this is, so liquid plus alpha give rise to a beta phase, so this is alpha plus beta region, and then you have liquid plus beta region. So this is the peritectic temperature at which the peritectic reaction happens. So this is a peritectic phase diagram. So Eutectic. Eutectic example could be, the very common example is lead tin, and isomorphous is, let us say, copper nickel. Peritectic, you see one portion, for example, in iron carbon on the top, then you can have several other systems. You also see this in various other systems. We will see some examples later on of these common alloy systems which show various kinds of phase diagrams. So in all these, in the two cases at least, we see that the liquid has a minimum melting point which is lower than, there is a melting point which is lower than the melting point of A or melting point of B, and this is called as, in this case, the eutectic temperature. Okay, so TE. So at this eutectic temperature, liquid of composition CE transforms into alpha and beta phase, whose composition is given by this point and this point. So this is C alpha and this is C beta. So basically you can say liquid of composition CE transforms at TE to alpha of composition C alpha plus beta of composition C beta. This is the eutectic reaction which one writes, and these are called as, so this is called as an invariant reaction. We will see the meaning of invariant a little later. Okay. In isomorphous phase diagram, basically liquid transforms into liquid plus solid. So solid starts appearing at this point, the transformation is complete at this point. So this is T start, this is T finish. Between TS and TF, for a given composition, you have liquid plus solid region. This is a peritectic reaction in which at peritectic temperature, liquid of composition CL, solid of composition C alpha. So liquid of composition Cl and solid of composition C alpha give rise to, so this is at temperature Tp, they give rise to a beta phase of composition C beta. One thing that you must note is that the composition of beta phase here is intermediate between the liquid and solid composition, whereas in case of eutectic reaction, the liquid composition is intermediate between alpha and beta phase compositions. So this is an important distinction that you must draw between the two phase reactions. And then there were two other phase reactions that we talked about. One was eutectoid. Eutectoid reaction is analogous to eutectic reaction, where one alpha phase at eutectoid temperature of composition C alpha transforms into two phases C beta of composition C gamma. So these are all solid phases. So this is basically solid state. So obviously it's a part of a phase diagram. It doesn't make a phase diagram complete by itself because it's only a solid state reaction. And then we had peritectoid. In the peritectoid reaction, alpha of composition C alpha plus beta of composition C beta transform and give rise to gamma of composition C gamma. So this reaction is depicted in this fashion. So you have alpha giving rise to beta plus gamma. So this is alpha plus beta, and here you have alpha plus gamma, and the compositions of beta and gamma will, this is C alpha, this is C gamma, and this is C beta. And this reaction is basically similar to peritectic reaction. Okay, so you have alpha plus beta, this is alpha, this is beta phase field giving rise to gamma, this is alpha plus gamma, this is beta plus gamma. So these are the three composition points. This is C beta, this is C alpha, and this is and this is C gamma. Okay, so these two are solid state reactions. So they are not there are 2-3 more phase reactions, such as monotectic, syntectic, etc., but we'll not discuss them because beyond the purview of this course as such. Now what we'll do is that what we have looked at is how to draw the phase diagram, what kind of phase reactions are there depending upon the type, defining the type of phase diagram. Now what we will do is that now we will see that what is the correlation between so in a phase diagram what you see is that so if you look at a phase diagram, for instance this phase diagram, in a phase diagram you see that if the pressure is constant, if P is constant, then we have two variables here, one is the temperature, second is the composition. So as a function of composition and temperature, what kind of phases exist, how many independent variables that we have at a given set of condition at a given point in the phase diagram, that is something which has to be determined. So basically this is so we can see that if we want to determine the number of phases at under given set of conditions, or we want to determine what kind of parameters we can change for a given type of phases and for a given composition and temperature, temperature could be a variable, composition could be a variable. So whether they are independent variable or whether they are dependent variable, that needs to be determined for a given, that is something that we can know about from the phase diagram. So basically we want to understand what is the effect of change in the variables on the phase stability, and alternatively what kind of independent variables that we can have given certain scenario is. So this is explained by a concept called as phase rule. Some people also call it as Gibbs phase rule. But in general it is known as phase rule, and here we are limited to binary system, mainly binary and perhaps unary systems, but it is possible to extend this into other systems as well. So in a two phase, so in a single phase in a single component system, so in a single component system, let us say the variables that we had were, we had temperature and we had pressure, because there is single component. So it would be interesting to see what kind of phases will exist when you vary temperature or pressure or both, and in what region. How does this vary as a function of so for example, if you have a phase diagram like this, let us say something like that, let us say, okay. So you have, let us say, alpha phase, you have beta phase, you have gamma phase, and this is, let us say, temperature and this is pressure. What kind of phases exist under various set of conditions? So that we can see with the help of this phase rule. You can have two phase equilibrium, for instance. So as we have seen in binary systems, you can have liquid plus solid, you can have solid plus solid, and so on and so forth. You can have three phase equilibrium. This could be liquid plus solid, for instance, in eutectic phase diagram, and so on and so forth. So so generally what we see is that if you look at the phase diagram, generally as the number of, so if you study single component phase diagrams and two component binary systems, there is a conclusion that you draw that as the number of phases increases, a number of variables that can be independently varied decreases. So this is something that we generally observe from phase diagram. So you can see that in case of a single component system, when you have single phase regions, you can vary both temperature and pressure. But when you go to binary system, there are certain regions where you can vary only one component. We will see the other parameter is fixed, and there are certain cases where there is no change in parameter whatsoever. So as we will see in binary phase diagrams, for example, if you have a 3-phase coexistence, you will see that those points are invariant. So generally a 2-phase region is called as an area kind of thing. When you have 2-phase coexistence, it's like it's a line, okay, it's a one-dimensional change in the parameter. When you have 3-phase coexistence, it's like a point. And when you have so 0D, when you have a single phase coexistence, then it's like an area, you can vary both the parameters. We will see that distinction between the three in the coming few minutes. So let's see. So to begin with, how to correlate. So we can say how to correlate phases, number, components, that is independent species, and variables for a given system. This is the objective of phase rule, how to correlate the number of phases, number of components in a given system, and number of variables that are available to you to vary independently in a given system to predict the phase equilibrium. This is the objective of phase rule. So to begin with, let's first if you have let's say m number of variables, okay, so you have m number of variables. These m number of variables are related by n number of equations. So truly independent variables are only, so number of are given by m minus n. So basically m has to be larger than n. So basically what it means is that out of these total number of variables, n number of variables are eliminated by appropriate solution of equations. So basically what you have is, if you have m number of variables, n number of equations where m is larger than n, the number of truly independent variables is m minus n. What it means is that out of this m, n number of variables are eliminated by appropriate solutions of equations, and basically they are not dependent, they are not independent variables. So let me give you an example. So if you have, for example, here by this definition, if you have m is equal to n, it means that you have a unique solution available for a given set of equations. So let's take an example. So we have 3 variables and 2 equations. So the first one is x minus y plus z is equal to 1, and second one is x plus y plus z is equal to 2. So we can see that we have 3 variables and 2 equations. Now we can rewrite these equations as, so if you just rearrange, you get 2x plus 2z is equal to 3. What it means is that you have x is equal to 3 by 2 minus z, and then you can substitute in one of these equations to get y, and this y turns out to be 2z plus 1 by 2. So you can see that the only independent variable out of these 3 variables is z, that is only one variable. In this case you can see that z is the independent. So by choosing a value of z, you can define both x and y for these three. So this is the basically summary of what I said in the earlier slide. Now put this in context of thermodynamic variables. So now let us go back to thermodynamic system. So basically it is a material where temperature is a variable, pressure is a variable, and then you have composition. So if it is a multi-component system, then you can have composition starting from xi, basically x1, x2, x3 and so on and so forth. Let us say total number of components is equal to, what this means is that you have C components, okay. So you have C number of components for a given system. So system has C components, and these C components give rise to P number of phases. So this is number of phases and this is C number of components, okay, both are number. So total number of what is total number of variables? Total number of variables is C multiplied by P. So you have C components, P phases. So for each phase you will have one of them. So you multiplied C with P. So each phase will have C variables. So C into P, total number of variables, plus temperature and pressure. So you have Cp plus T is the Cp plus 2 is the total number of variables, and this 2 comes from temperature and pressure. So now let us see how do we look at this in the context of phase equilibria. So the first condition for a given alloy system comes from basically mass conservation, okay, because whatever you do, your mass mass of all the elements in a given system is conserved. So which means that x1 in phase 1 plus x2 in phase 2 plus x3 in phase 3 and xc in phase 1, sorry, this is phase 1 not phase 3. So in one phase, in phase 1, x of all the elements, the weight of all the elements is mole fraction of all the element, weight fraction of all the elements is equal to 1. So sum of mole fractions of all the components in a single phase is equal to 1, and if you have number of phases as P, as we defined earlier, we can write this as x1 2 for the second phase, and if you keep writing this for number of phases, then you can say that this is x1p plus x2p plus x3p plus xcp is equal to 1. So how many equations will this give rise to? This will give rise to p equations. So total number of equations that you obtain out of this will be equal to p set of equations, okay. Now the second condition is comes from chemical equilibrium. Now chemical equilibrium says that, so if you have, let us say, phase 1, okay, and let us say you take for a particular element dxi and you transfer this to phase 2. So there is a transfer of mass between two phases, let us say, and you add here dxi, okay. At equilibrium, if the equilibrium is maintained, then delta G is equal to 0, which means at so let us say dG is equal to 0. What it means is that basically no transfer of mass. Okay. So, for mass transfer to happen, so if let us say we are considering the transfer from 1 to 2. So, if dG for this process is less than 0, which means it is spontaneous, one to 2. So, dG 1 to 2, or if dG 2 to 1 is less than 0, then you have a spontaneous transfer for 2 to 1. Okay. So, this is the free energy change that you are going to happen. Now, free energy will change, the total free energy will change as you change the mass from one phase to another, you have some changes in the free energy. So, if let us say if Nji is the number of moles of component, let us say jth component in phase I. Okay. So, it is ith phase and jth component, and let us say Gi is the free energy of, so we are saying that it is phase I. Okay. So, free energy of phase I is Gi, and Nji is the number of moles of component J in phase I. So, let us say the transfer happens. So, upon transfer, of del J del Nji, so very small amount of jth component from I phase to another phase. Okay. So, upon transfer of del Nji of J component from phase I, so I write change in the free energy, let us say so I can write delta Gi is equal to del Gi divided by del Nji into delta Nji. So, this is the incremental change in the free energy of ith phase upon causing an incremental change in the composition of component J. So, this is basically the, if you recall, this is called as chemical potential. So, basically this is mu J in ith phase. So, chemical potential of jth component in ith phase. So, now how will this affect the other phase? So, this amount goes to phase K. So, changes in its free energies for kth phase. So, delta Gk is equal to del Gk divided by del of Nj k into delta Nj k. So, this is the free energy change that happens when the element has entered into phase K, but the amount of solute that has entered the phase K is same as the amount of solute that has left phase I, which means del Nji is equal to minus of del Nj K, because the mass is conserved. So, this is mass conservation. Okay. So, now what we will do is that we do not have time now for doing this, but what we will do is that we will now take this further to establish the free energy condition, that is the total free energy change for the system to be equilibrium must be equal to 0. So, if that happens, then what is the condition at which we arrive? Okay. So, we will do that in the next class. So, what we have done in this class is we have basically started the procedure for establishing the phase rule conditions, basically to find out the phase equilibrium in terms of number of phases, number of components and number of components with the number of independent variables that are available, and to find the to correlate them to find the phase equilibrium. So, we will further dwell on this in the next class. Thank you.